Hello, hello, hello. I'm teaching a class. I'll be teaching a class in calculus first semester, and this is a review of limits, which is pretty much the first thing you cover when you start calculus. And the reason we do limits is it's a way of showing that the certain equation or function is continuous, and later on we can use the same concept to see if continuous means if you like put your pen and draw from A to B and you don't lift it, we call that continuous. And then we have to see if it's differentiable, meaning if it's a slope, if it has a slope everywhere along that continuous line. So the next test of differentiality is going to be looking at the limits of a derivative and seeing if they're the same from left and right. Never mind all that, but the point is that first we're going to be using it for testing whether the function is continuous, and then the next is if it's a measure of how smooth it is, sort of. If it's too spiky, there's no such thing as a slope of the top of a mountain right at the spike. Okay, so that's all we're doing. So this is the beginning, and what I'd like to show you is, in fact, what we're looking at here is a particular problem you'll see a lot in AP calculus. The sine of x over x equals 1 as x gets closer and closer to 0. Now you can see we have a problem if it actually gets to 0, because we'll have 0 in the denominator. Oh, we need a trick. We call it a kind of a squeeze theorem trick, and I'll show you how it's done. And first of all, what we have are three areas of how it's created. So you see that this area here, the black triangle, is simply B as the base and A here, but R is the radius of that circle, unit circle, so R is equal to 1. Then we have this area of a sector of a circle, you see, where R equals 1, and this is the arc length. Okay, so we need to take that area. I think you would agree that the area of the red, or of the arc, of the area of that section of the circle is bigger than the area of the black triangle. I think this is believable. And then we put yet another triangle, which is bigger than all the two. It's the biggest of the three. And again here we'll have something like this measurement up here. We can call it, for example, A. Let's see, I'll call it A prime, just to distinguish between this A here. Actually, that one's a little bit harder to see. Let's see if I can do it on the other side. So let me get rid of this, and then I'll go like this. Okay, and so what I'll do is I'll call this guy here a little a. Let's see if I can do it. I'm actually have a mouse, or I'm using my thumb to write. Okay, anyway, there you have it. So basically I'm going to set up these three areas. And so the area of this triangle will be less than the area of sector 2, and would be the less of the bigger area, blue area, right? In this case, R is equal to 1. And in this case, we have also that this is going to be this from here to here. You can see is also R, right? And this is also R equals 1. I could do better than that. I could move the R even a little closer. Bear with me here, because it's always a challenge. It's like I feel like I have some sort of bodily issues. It's not. Okay, here we go. I'll just call that R. Okay. Okay. Alright, and I'll obviously over here is R equals 1 too, right? So, because this is on the unit circle. And this one here, well, I have to recall it, but I shouldn't be calling it R. We can call it, let's see, because that's bigger than R. See, from here to here is not R anymore. So let me get rid of this here, because I made a boo-boo. So I'll get rid of the boo-boo. And we can call it, I don't know, whatever we want to call that, the largest one. So we can call it, I don't know, C. How about C? Or we'll figure it out. Oh, then I'll call it C. Right here, just to name something. Right? Yeah, C. Okay. So I'm going to compare the three areas, and then I'm going to let X approach 0 and see where they squeeze the middle guy into an answer. All right. So let's take a look at the area of the black triangle. It's half of a rectangle, right? What's the area of a rectangle? Well, it's A times B. and then we divide it by 2. See? That's that area. Now, how about area of a sector? Well, I'll show you in case you've forgotten. We can look over here. Let's see if I got it over here. Yeah. So it's easy enough. So I'm looking at the section. This is angle X, right? This is R and R, and this is what we call the arc length. So I set up a ratio. I said X is to the whole degrees, all degrees. So X is to 360 degrees. So that don't look so good. Let me see. So if I were to open X, so X is equal to, so it's this angle X right here. See it? X divided by the total amount of degrees in a circle. As the area of this sector, we call it AS, is going to be to the total area of the circle, which is pi r squared. And if you need help with that, I can do some more talking about how to derive it. But pi r squared is a famous equation for the area of a circle. So I'm taking our sector of the circle and dividing it by pi r squared. Now I'm going to change 360 to radians, and this is how you convert it. 360 times pi over 80 gives you 2 pi. So I'm going to change this guy here to, I'll be just putting this, it's the same thing, it's just measured in radians opposed to degree. I'll put 2 pi. But anyway, I'm changing 360 and I'm renaming it to 2 pi. Okay. Actually, 2 pi is equal to 360 degrees. Okay. Okay, when I solve for that, then I want to solve for the area sector, correct? So the area sector is, I want this by itself. So I'm going to multiply both sides by pi r squared. Remember, this is 2 pi now. So when you do that, you're going to get the area of a sector is going to be, area of a section is this over 2. And you can see why, basically, because you can see that the pi's will divide out, right? When I multiply it over here by pi, this pi divides out. And, well, okay, so now I got r, but r is equal to 1. So 2 copies of 1, or r squared is 1. So all I got left is, on top here is x, my angle. And down below I have 2. So I have, and then what I have on top, I got r squared, right? But that's equal to 1. So anyway, the area of a sector is pi r squared. In our case, we set r equal to 1. And when you set r equal to 1, right, then that sector can be described as pi over 2, which is 90 degrees. All right. Well, that's not a very good 2, but you get the idea. Now let's take a look at the bigger triangle. The bigger triangle is right here, see it? Okay, so let's take a look at this guy here. I'll call it, remember we're calling that A prime. So let me call that right here. So this is A prime, right? That's this guy right here. Okay, A prime. And if I call this A prime, if I take the definition of the tangent of this angle x, this is a degree symbol. Okay, the tangent of x is A, right? Just this little A here, see it? This whole thing measures A. I would calling it A prime. A prime over R. Here's the R. And so R is equal to 1. So another way of saying A is R tangent of x, or setting r equal to 1, right? And another way of writing tangent of x is a sine over cosine of x, okay? That's just a review. Let's go back and check it out. Okay, so here's the area of the little black triangle, the sector of the red, and this guy, remember this height here is tangent of x. So I know that we can say over here that the tangent of x is divided by 2. Because we have, because of the equation that we had over here, remember? So this is pi r squared divided by 2. In our case, r is equal to 1. So once I solve that, and I put it in here, so I got this right. And once I put it 1, I'm sorry, over here, there it is. R is 1, see it right here? 1 times the tangent. And so, 1 times the tangent of x. Okay, so it's just the tangent of x over 2. So now I'm going to multiply, as you see here, all terms by 2. So 2 will divide out, 2 will divide out, 2 will divide out, right? So now I'm starting to make this sandwich, or this is, remember r is equal to 1, right? So I have two copies of 1 is 1. I call them copies. So a times b is less than x, 1 to the squared tangent of x. Okay? But remember, we can write tangent of x as sine over the cosine of x. So that's nice, because that, alright, now that's sine over cosine. However, I'm going to divide all 3 sides by the sine of x. And I'll show you why. Excuse me. Okay, and so I'm going to divide everything by the sine of x. So I have the sine of x over ab, x over the sine of x, and this divides out. So now I'm going to flip. So I'm going to take the sine x, flip it up, and bring the ab down, and look what happened. My inequality flips over. And so over here I have sine x over x, so that flips over, flips over, flips over. Now let's take a look at the sine of x as a times b, right? So now we have this cosine of x times b. So one way you can think about it is that, so we're going to show that this is going to end up being the cosine, 1 over the cosine. And then I just flipped it, right? I just flipped it. Now, the reason I'm flipping it is I'm trying to make it look like this right here. See it? Okay, now I flipped it. It's starting to look at it. I had to change it. Now, what I was left is cosine in the denominator. Now it's in the numerator. Now that sine is up here, right? But what's going to happen is over here we have the cosine. And let me show you what I mean. So I know that this definition of sine is going to be, you remember r is equal to 1, right? So the definition of sine is going to be a divided by 1, and the definition of b, right, is going to, the cosine of x is going to be b divided by 1. So a and b are simply going to be equal to their, if you keep in mind, sine over cosine. So I can rewrite this thing, right, as, I can rewrite this as being the sine of x, the sine of x, bear with me because I'm using my thumb here, the sine of x times the cosine of x. You get it? I'll multiply those two together. I'll put it down here, right? So, but remember I flipped. So a is going to be, as you see, the sine, and that's cosine. So it gets the sine. Well, that will go out with this because a is the sine of x. Yeah. And so now I have 1 over the cosine of x, x. So it turns out that I'm going to go up here for the solution. So now I'm going to take the limit, and let's just see how the function behaves as x gets closer to 0. And so as x gets closer to 0, so 1 over cosine, I think you may need to know that when cosine is 0 is equal to 1. And over here we're trying to figure it out. Well, look what happens over here of cosine. As x equals to that approaches 1. So if that's 1 on the left and that's 1 on the right, guess what the limit of sine over x is? Yeah, it's this 1. Now let's take a quick look at the okay, before I finish, I just wanted to show you what this function looks like. It's at Desmond. I just graphed the sine of x over x. So if I zoom out, you can see that this is the highest part, but it's oscillating like a sine function. It's starting to taper out as it goes out. But we're looking at what happens in this equation as x approaches 0 from the right. As x approaches 0 this way, you can see that the y limit approaches 1. As x comes from this way, then the y limit approaches 1 again. So we can say that if we show that it's equal to 1, then we can say it's continuous because it has the same limit from both sides. That's it. Okay, thanks.